No, this is the Unit 2 exam paper question 6. Now I'm going to go very quickly through this and through question 7. I'm to do in about 10 minutes, purely because kind of restricted on times. So this is the graph you're given, and one of the first questions you're asked to do, well, the first question is to draw a line of best fit. Now what you do is you draw a line through the points, and it sort of curves at the top. It should go through most of the points. And now it says in the mark scheme for 2 marks, you need to go as a straight line, horizontal, up to about, this is 10 times 10 to the minus 7, so up to about 4 times 10 to the minus 7. It has to be straight, and then it can a smooth curve afterwards. So basically that's, I can't really explain it more than that. The next part, it says 6a part 2. It says calculate the gradient of the graph. Use the graph to calculate the initial gradient k for this example of the cable. Now it says the initial because obviously this doesn't follow Hooke's law. It's changing gradient, changing proportionality. So it reaches limit proportionality, or its elastic limit, whatever you want to call it. So basically we can draw a gradient anywhere along the flat section of the line. So what you need to do is draw like a dotted line to the line of best fit down, read these 2 points, work out the gradient. I'm just going to use the example they give you. So we know F equals K times delta L. So K being the gradient, K is equal to F over delta L. That's how we know K is the gradient, And if we do that, we could get, it says 2.55 times 10 to the minus 6, which is the height, which is the force. So it's 10 to the minus 6 over the delta L, which should be that value there, and that is 5 times 10 to the minus 3. And then that gets you a constant proportionality K, spring constant, which is 5.1 times 10 to the 7 plus 7, and that's newtons per metre. You need to make sure you have the units on the end there, otherwise you won't get the mark. And you can have plus or minus 2%, so plus or minus 2% of that, and you can work that out for yourself. Now I'm just going to make sure you can actually see this before I continue with the sort of little bit of fun. Zoom, hopefully that's a bit better for you to see. Probably isn't, but never mind. So anyway, that's the first part of the question. 6a part, 6b, sorry, done 6a. I'm going through this very quickly, as I said, because I want to get this out of the way so I can do the next past paper. Because I don't think this bit's too difficult at the end. 6b, it says, let's read out. No, you can read if you want to. It says, the breaking stress breaks when the extension of the sample reaches 7 millimeters. Calculate the breaking stress, given an approximate unit. So we know delta L equals 7 millimeters, That's my point. I've just sort of gone on to try and prove it there. Let me just see what the graph is. Load. Calculate the breaking stress. Alright, okay, so we've got delta L. Just making sure I've got this right before I go off with it. So it says calculate the breaking stress. Now the breaking stress, as you know, stress is tension over area, and strain is delta L over L, and you combine them to get Young's modulus, but it's asking for stress, so we know stress is F over A, force over area, is it? Or tension over area, it doesn't really matter. And if we read up from 7 millimeters here, we get the newtons, so you need to draw another line on the graph from 7mm up, read the force and plug it into this. Should you calculate the cross-sectional area, if you haven't done already, which is just pi times diameter squared over 4. And the force you should have read up as 2.8 times 10 to the 5. The area, pi times diameter over 4, should got you 2.5 times 10 to the minus 3. Obviously, you could have a couple of values for the force, depending on how you've... no, it says 2.8 only, sorry. And then that gets you 1.1 times 10 to the 8 pascals. I almost said 9. And you can change that into gigapascals or whatever you want. So it'd be 0.11 megapascals, I think it is. Or gigawatt, I think it's megapascals. Not 100% on that. I'd just leave it as pascals if I was you, because it saves you getting into bother of mixing up your units at the end. So that's 6B. 6C, it says when in a cable car system, 1,000-metre length of this cable is used. Calculate the extension when a tension in this cable is 150,000 newtons. So we know the tension is 150,000 newtons. So I get out of the way a little bit. And it says the so tension is the same as the force. You need to remember that. And it says the cable system is delta L, which is 1,000 metres. It says work out the extension of the cable. Sorry. Length. So that's just the length. Sorry. And our K is 5.1 times 10 to the 7 newtons per metre, as it hasn't actually changed. Sorry, I think I might be running out of time. Right, I've got another 2 minutes, we can get this done. Sorry. So that's our K, so we just plug in our numbers. F equals K times delta L. So delta L, so I'm doing it in different colours so it's a bit easier to see, is F over K. And if we plug our numbers in for F over K, it'll be 150,000 newtons over 5.1 times 10 to the 7 newtons per metre. I'm not going to write that in, but that should get you 2.94 times 10 to the minus 3. And that's your metres. That's your extension. So that was really quick for question 3. Trying to save time, as I said before, so we'll see you in the next video. So no banter this time, unfortunately.